All right, you've been listening to Jay-Z and Linkin Park from their album Collision Course. The song is Numb Encore, the amended version. And the reason I picked it is because of the word collision. So we're talking here about kinetics, and on a molecular level, that is explained by the physics of collisions between particles and how they react. And that album, by the way, is just simply awesome. All right, so what's on deck for today? By the end of today, which is 4 lectures as I have them split up, you should be able to explain how temperature, concentration, and catalysts affect the reaction rates on a molecular level using the collision model of reaction dynamics. This will make sense soon. And if I give you some initial reaction rates, you're going to be able to tell me how a reaction rate depends on the concentration of a reactant. And using that same data, you're also going to be able to put together something that we like to call a rate law. So let's get to it. All right, what are reaction rates? So stoichiometry, which we've studied up to this point, tells us how much of a product you should make in a reaction. The enthalpy change, the energy change, something else, will tell you the heat released or taken in by a reaction. And what it doesn't tell you, though, is if any of those processes will happen anytime soon. And that's where kinetics comes in. So kinetics is studying the rates, or how concentrations change with time, of chemical reactions. All right. So, I'll give you a sense of scale here. What's the slowest reaction that we can study? Well, this is one that more or less comes and goes in about 5 years. Why is that? That's kind of the life of a graduate student. What's the fastest reaction we can study? That's one where things come and go on the order of 10 to the minus 14 seconds. And I say this partly in jest, but this is, a 22 order of magnitude range. Not a factor of 22, but a 1 followed by 21 zeros factor change. The other thing that makes this partly in jest is that there are ways in which reactions that occur over a much, much longer time scale than 5 years, like billions of years, can be studied, and geologists and astronomers are very good at that. And quite frankly, just because this reaction, that you're studying comes and goes in 10 to the minus 14 seconds, it's probably still going to take you 5 years to have that characterized, because studying reactions this fast is an art unto itself. All right. So what exactly is a rate? So let's get the mathematical definition out of the way here. Any rate is strictly defined as a change in something divided by the time it took for that change to occur. In complete math speak, it's delta something over delta t. So as it has shown for a couple things here, this delta here usually indicates, or always indicates, change in final minus initial, and this little t here is what we usually use to denote time. And finally, so just to give you an example, let's say the rate at which the pit sells basketball tickets back when we could watch basketball games, at least live games. So I could do this and define the rate as the number of seats that are filled at 10:45 minus the number that you sold at 8:15. So this would be the change in seats sold, which presumably is a ticket per, divided by the time over which it occurred. And just like it has before when we've seen it, the notion of that delta always means final minus initial of whatever you're talking about here. All right, so now we've got it set up, and it's just a matter of crunching the numbers at this point. So we've got, let's say, if at 10:45 you had 12,874 seats sold, and back at 8:15 you only had 2,147 seats sold, the time interval is 2.5 hours. So that would give you a total of 4,300 seats per hour. And note that, there is, in any proper rate, there is always a time component to it, per second, per hour, per year, something like that. All right, so in the next video, we're going to talk about reaction rates and how we actually define them in terms of chemistry. See you then.